Yes, Evan.
In the formula, or in the equation, y equals 1/2 ap squared,
Yeah.
a is just the acceleration of the particles as they're getting closer to the plate, top plate.
Yeah, as their vertical acceleration as
So
they're
how
moving through the
much they're going
plates.
faster, and that's just
Right.
a constant. That's just going to be a constant, like it's a constant for how something keeps going faster.
Right. I mean, in this case,
More it's
so
falling.
you're keeping the charge on these plates constant. And so you've got a constant electrical force that's causing these things to move up, to accelerate vertically.
But they're also, the closer they get, the stronger the force. Oh.
No, because it's a
Because the
bottom one
repulsion.
pushes too. So actually the electrical force between two flat plates like that, it's constant.
No matter where you are.
Yeah.
Like since the acceleration is just measuring how quickly it gets to it's going up,
Right.
couldn't you just like put sheets like if you're the plates, couldn't you measure how far they are here and how far they are here and just incremental areas and then calculate? Like the plates, you can measure at one point how close they are and then how close they are, like maybe a centimeter inch away and how close they are another inch away.
Oh, I see. Um, uh, just by observing how they're moving, yeah, you could actually get the acceleration that way if we could actually observe them.
But would you have the plates cross them?
Only when they hit the far screen. That's the only thing that Thomson is seeing. He never sees the charged particles go through these plates. Okay, he only sees where they hit on the screen. So that's, yes.
Couldn't you like move screens in between them to see?
Oh, yeah, put them through various size plates, basically, and show how it moves up. Yeah, you could do. You could do that. What Thomson did was actually a lot easier, though. I mean, what he did was he just charged up his plates and saw, how much they were deflected by the charged plates, and then it was pretty easy for him to cancel it out with the magnetic field. And then you can get the I mean, he could complete the whole calculation that way and calculate the quantity he wanted, which was just the charge to mass ratio. So the now that's where we ended last time. Okay, so let me continue this story about the discovery of the electron now. Now, when we ended this morning, we had gotten to this this final equation. Let me write it down again in all of its glory. Thomson had shown that the ratio of the charge of the electron to its mass is given by 2 y, which is the amount of vertical deflection when the electron goes between the charged plates. Let's see. Let me. Yeah, I was just going to write it in a slightly different way. We had E, which is the electric field, over L squared in the denominator here. And then we had the speed squared up top in the numerator. Well, The speed we showed, though, is the electric field squared divided by the magnetic field squared. So he has a final equation, which is there, you can write it like that, which is 2y times the electric field divided by L squared B squared. Now, and like I say, this electric field, that's just directly related to the voltage and the distance between his plates, which he knows. And the B field can be calculated from the current in your coils and so on, so that he's using to generate this magnetic field. So he's got everything, and I told you this crazy number he comes up with, which is 1.76 times 10 to the 11th coulombs per kilogram. Now, coulomb is just a unit of charge. Actually, the way that's defined is if you have, remember the unit of charge that I told you about when we were talking about current was an ampere. Okay, I mean, you've all heard of amps. Okay, that's the unit of current. Well, if you have 1 amp go through a wire for 1 second, the total amount of charge that's gone through that wire is called a coulomb. Okay, so that's what a coulomb is. Now, it turns out that's a big unit of electricity. So let me try to relate that to something that you know about. When we did, earlier in the year, when we did experiments on static electricity, you probably all saw Mr. Van Dam take a balloon and rub it against his head, right? Okay, to get a static charge on it. Well, if you take a balloon and you rub it really hard against your head, the most you can get on it, usually the most you can get as far as a static charge goes, is about, I mean, it's less than 1/1,000,000th of a coulomb. Okay, it's about, say, 10 millionths of a coulomb. So let's say the electric charge on balloon that you get a good spark off of, okay, is about equal to 10 to the -7th coulombs. Yes, Troy.
How many coulombs would be in a lightning bolt?
Oh, lots. That's a good question. I was actually going to tell you a little bit more about lightning at the very end of this class, so I'll try to include that information. But yeah, I believe that if you average the lightning storms all over the earth, you know, then there's always some going on. The total current that's going from the atmosphere to the ground is something like, if I'm remembering it right, about 40,000 amps. So every second, the amount of charge that is flowing from the atmosphere down to the ground is like 40,000 coulombs. Okay, so I mean, it's, if I'm remembering that number right, so it's a lot. Okay, but normal kind of charges, I mean, even when you get a really good zap off of a car door or whatever, you're getting, say, 10 to the -7th coulombs. So let's put this this number that that Thomson came up with in those units. And I worked this out, and I got the following. See if this means anything more to you. 10 to the 15th, say, let's call them balloon sparks per gram. So what does that mean? That means that if you had a million billion of these balloons that you had charged up against your head. No, it's more than a trillion. A trillion is only 1,000 billion. This is, let's call it rather than a million billion, you can call it 1,000 trillion if you like. Yeah. Okay, if you had that many balloons that had all been rubbed against Mr. Van Dam's head, then, and you got sparks off of all of them, the total amount of electricity from all those balloons would be the electricity that you get from 1 gram of electrons. 1 gram of these negatively charged particles that we're talking about, that Thomson discovered. 1 gram of these electrons. Where can you get a gram of electrons? They should sell them down at the mall at the Discovery store. Yeah. No. 1 gram of 1 gram of pure electrons would be a powerful force. Another way to look at this is that spark that you get from that charged up balloon, or you feel that zap, the total amount of electrons that has transferred from the balloon to your finger is 1,000 trillionth of a gram. It's a very, very small weight of electrons that you've actually gotten zapped with, but you feel it nonetheless. So electrons are incredibly powerful things, is what Thomson has discovered. I mean, they have an enormous amount of electric charge per unit mass. Okay. But Thomson wasn't able to figure out what that charge was. He just knew charge per mass, right? He doesn't know the mass or the charge. He just knows the ratio of the two. So somebody had to come along and figure out how you can actually figure out the charge on a single electron, and therefore figure out the mass of a single electron. And let me see, does anybody remember when Thomson did this experiment? Daniel? 1897, right. And less than 15 years later, some clever physicist figures out how to actually calculate the charge and therefore the mass, not just the ratio. So I want to now tell you who did that and how he did it. And his name is Robert. I'm going to switch markers again. Robert Millikan. And I believe he actually did this experiment in well, he started, it was a complicated experiment that actually took him a couple of years to perfect, but he started doing it in 1909. I don't think it was actually, his results were published until 1912. But here's the idea. Let's, before, in Thomson's experiments, we had these electrons flying at high velocity through these plates. Well, Millikan thinks, what if we could get them to just loiter between the plates? What if we could put an electron in here and get it just to hang out between these plates? Because what we're going to do, I mean, the electron is charged negatively, right? If we charge the top plate positive and the bottom plate negative, okay, that's what Thomson did to make the electrons go up, right? But let's say we try instead not to make them go up, but to balance the electrical force that's pushing them up, let's call that F sub E, with the gravitational force that's pulling them down. You know, that's what Troy asked about this morning was, you know, how can I get away with ignoring the gravitational force? Well, it turns out that these electrons are so light and they're so strongly charged in comparison to their weight that you can, for the most part, ignore the, in Thomson's experiment, you could ignore the gravitational force. The electrical force was the only one that was significant. But Millikan has the idea of trying to make some adjustments to that experiment so that the two forces actually balance out. Troy?
One that's simply going at really high speed that way.
Oh, well, he's going to change that too. So what we wanted to do, somehow we want to put an electron, here's the trick. How do we put an electron in there and then get the electrical force and the gravitational force to be about the same magnitude? Now, in order to get the gravitational force as big as the electrical force, we're going to have to tie weights to this electron, right? Okay, so he figures out how to do that. You tie ankle weights to it or something. Yeah, little microscopic weights. I'm going to show you how he does that. Then, how do you get it? How do you get it in there so that it's not, you know, just flying through, but it actually stays in there? Well, here's what he does. He solves both problems that he has. How do you get it in there and tie weights to it and have it just hang out in there? He does it by cutting a hole up here, and he has a little spray gun that he can squeeze here, and he's got some oil in there. Okay, so he sprays out this oil. I mean, he squeezes this thing, and a bunch of little tiny oil droplets come flying out. Oil sprayer. Now, when those little droplets of oil come spraying out, just the friction of that spray, some of them pick up some static charge. They pick up a few electrons. So those are the weights the weight that I was talking about that he attaches to these electrons is these little oil drops. Okay, so he's got little oil drops that have like an electron or two or three or, you know, a dozen maybe, but a few extra electrons on them. That's the static charge. And some of them fall down through this little hole he's got in the top positive plate. Okay, now, when these little oil drops with a little bit of static charge on them get in between these plates, what Millikan sees is that a lot of them are, you know, instantly either fall down onto the negative plate or fall up onto the positive plate. Now, the ones that just move up fast and hit the top of this positive plate, those are the ones that had a lot of electric charge. They had a lot of electrons on them, right? The ones that, say, didn't pick up any electric charge, they'll just fall down. But in every time he sprays some of his oil drops in here, there's a few of them that have the right amount of charge and are the right weight such that the electrical force and the gravitational force will balance. That's right.
What would be a continuous stream of electrons from the battery, the plate, the negative plate? So would they keep on? I mean,
Oh, would they fly off this negative plate?
I mean, like from the other end of the tube that's sending the
Oh,
electrons out.
well, he's gotten rid of all that. Okay, his entire apparatus now consists of this. I've drawn these plates here. He's just got a big battery here. Yeah, let me just draw it that way for now. I'm going to fill in a few of the more of the complications later, but this is it. You know, he doesn't even have a vacuum chamber. This isn't even enclosed in a tube where the air has been pumped out. This is all he's doing is, you know, he charges up these plates strong with this big battery of his, and then he just has this oil spray, and some of the droplets get in here. Some of them have some static charge on them. And now the one thing I should say, actually I'll add one thing to this drawing now. He has something here in his battery circuit that's called a variable resistor. Okay, it's just a resistor, like a piece of carbon or something. But he can hook a variable amount of that carbon into his circuit. So let's say he has a chunk of say he has a chunk of carbon here, and he can hook his wire up to, let's say if he has it hooked up to the middle of the carbon, then the electrons have trouble getting through this carbon. Okay, so that's going to slow them, that's going to cause some resistance and drop the voltage, decrease the voltage on the charge on these plates. But he can hook up his wire to the middle of that resistor, or he can include the whole resistor, or he can include just a little bit of it. So he can, in effect, he has an easy way to adjust the charge on these plates. Okay? That's so when he sees an oil droplet, let's say, in here that is falling down slowly, well, if he wants to stop it and raise it up, all he has to do is, well, he wants to increase the electrical force, right? So he wants to increase this charge. So he wants to include less of this resistor in his circuit. Okay, so that's he has just an easy way of adjusting the charge on these plates and adjusting the electrical force. Troy.
In this one, where did the electrons go? Just from
They're created by it's probably like resistance against the nozzle and even the air. In other words, this oil is sprayed out of this nozzle, and it just encounters its friction against the nozzle itself and the air, that some electrons will rub off on these drops. So it's the same way that the balloon gets charged when Mr. Van Dam rubs it against his hair. It picks up some electrons from his hair. Okay, so now let's say we've got a drop in here, and it's just hovering. Well, in that case, you know that the electrical force it's happening again. Switch markers. The electrical force has to be equal to the gravitational force, right? Well, what's the electrical force? In terms of either the electric field or the voltage, whatever you want to, Evan.
It's the charge times the electric field.
Right, so it's the charge times the electric field. Or we can write that as the charge times the voltage divided by the distance between the plates. Okay. Since batteries usually come just marked in voltage, well, we'll use this equation here. Now, I should write, actually. Remember, I've been using V for speed and V for voltage. In this case, V equals voltage. Now, what's the gravitational force on this little oil drop? Troy.
gravitational constant times the mass of the electron times the mass of the Earth, all divided by the distance from the center of the Earth squared.
You're trying to give me the full Newton's full equation for gravity. Well, we can bypass that in this case because the Earth is a constant; it's not changing, and all of that is embodied in this constant gravitational acceleration that's 32 feet per second squared, right? So that takes into account the Earth. So we don't have to worry about that. All we need is the mass of this drop multiplied by that 32 feet per second squared, the gravitational acceleration. That's which we usually call g, right? So, and let me write up here. M, in this case, is not the mass of the electron, right? It's the mass of what?
The electron and the oil.
Yeah, the oil drop. I mean, that's the object that we're looking at, and that's what gravity is pulling on. Okay, so Now, well, this doesn't look too bad. Let's rearrange it a little bit. The charge on the electron now is, say, D, which is just the separation of the plates. G, I mean, D is easy to measure, right? You just pull out a ruler. G, we know, Galileo told us, 32 feet per second squared. Divided by the voltage, that's easy enough. We know what voltage our battery is. So multiplied by the mass of this drop. Now, Evan.
The gravitational constant is just, it's the amount of force on a specific mass. It's how it increases over time.
Yeah, it's the rate that the speed increases due to the pull of gravity. So and it's always the same on the surface of the Earth. I mean, if I drop this thing or whatever I drop, it always falls at the same rate, right? So that's what that G is. It's just that everything that falls on the surface of the Earth always increases in speed by that 32 feet per second each second. If we were on the moon, that number would be, off the top of my head, I don't know it, but maybe it'd be down around, 10 feet per second. Okay, now, what problem do we have with this equation here? Daniel. You still have M. How do we figure the mass of these drops? Now I'll actually tell you a little bit about what Millikan actually did, which is he had to do something a little more complicated than what I'm about to explain to you. But I want to first explain the simple way that he started out trying to do it, which turns out not to be real accurate. So he ended up doing something more complicated. But I'll save that for later. Simple way. Well, do you have any guesses? Now he's observing these drops carefully through, a little telescope that he has. Troy.
Find the size kind of and know the density from just having the density in the oil spill.
Exactly. Troy hit it on the head. If he knows the density of this oil, then all he needs to know is the size of this drop. If he can estimate the size of the drop accurately, he can compute its mass, right? Because let's say water is has a density of 1 gram per milliliter, right? Well, let's say this oil that he's using is, it's twice as dense as water. Well, then it's 2 grams per milliliter. So if he knows the volume of this drop and the density, he can compute the mass. So that's exactly what he does. He writes this equation for these drops are approximately spherical. So there's the volume of one of these drops, right? And if I say I use there's a Greek letter called rho that is looks a little bit like a P, that's often used for density.
How does it look? What is it just a P?
Well, it's sort of, rather than a P like that, it's sort of like that. Yeah, yeah. Anyway, so, and rho is just mass density. Say, you can put that in grams per cubic centimeter. Now, so all he needs, and this is easy to measure. Okay, if you got your oil, all you have to do is take a certain volume of it and stick it on a scale. So then you've got the density. So all he needs to do is measure the radius of these drops. And he can know their mass. So let me see. He does that, and let me just cut to the bottom line here now. The charge that he comes up with. Well, first let me explain one thing. Sometimes he would spray these drops in here, and he would get like a little drop and a big drop that both balanced. Now, why would that be? What's going on in that case? Nee.
A balance of the right amount of electrons in each of them to make up for the weight.
Right. Obviously, the big one has to have more electrons than the little one, right? So that they can both balance. If the big one weighs 5 times more, then if it has 5 times more electrons, then it'll still balance. So when he calculates, Millikan really worked hard on this experiment. For years, he observed thousands of these drops. And he would calculate the charge on each one, and he wouldn't always get the same number. But the crucial thing was that what he got was some integer, we're going to call it n, multiplied by 1.6 times 10 to the negative 19th coulombs. Okay, in other words, this is a little tiny bit of charge here. This 1.6 times 10 to the negative 19th coulombs. What he found was any drop of his that he could suspend between these plates always had at least this much charge on it. And any drop that he observed always had some integer multiple of this charge. It could be just this charge, or it could be exactly twice that charge, or exactly 3 times that charge. So, obviously, this is the charge on the electron, right? Electrons are particles. They only come in one amount of charge. And you can have one of these particles, or you can have 2, or you can have 3, but you can't have, 1.5. It's the same sort of thing we saw with atoms. Sure.
Well, could they have been smaller than that, like let's say half, and because you're just going to get a smaller size than that?
Well, no, could there be a smaller amount of charge than this? He observed, like I said, this thousands of drops, and all of them had an integer multiple of this charge. So, I mean, he worked with fairly small drops too. I mean, I guess I'm not getting your question. Why do you think there could be a?
Well, I mean, it could just be like half of that, so they would still all be integer multiples. Maybe that's like. not
Oh,
making sense.
yeah, but if that were true, then it would have been a fantastic coincidence that all the drops he observed had even numbers of electrons on them. In other words, what would have had to have been the case, if what you're suggesting is the real charge on the electron is really half this.
I mean, not
Wait.
exactly, but could it have been?
Well, let's just take that case. Let's say that the real charge on the electron was half this. And so the drop that Millikan thought only had one electron on it, Troy's telling him he really has two. Okay. Well, how would Millikan respond if you told him that? Evan?
If that was only half the charge, then you could possibly end up with 3 halves of that, or it wouldn't always have to be in.
Right. I mean, according to your hypothesis, Troy, if it were half this, he should be able to come up with a drop that had 3 of your electrons on it. Okay, that would have 1.5 this charge. He never sees that. So the only way your half electron hypothesis would work is if for some reason these half electrons always teamed up and went around in pairs, because there would always be 2 of them on a drop, or 4 of them, or 6 of them. You wouldn't have any odd numbers. Okay. So Millikan has really strong evidence for this. Now, let's put this. Let me see. Let's put this in perspective here. This is a really, really small charge. Yes.
Well, I can run a little, but it's sort of a question we had. It's a little unrelated, but it's how you could have. If you should I ask it later.
No. Go ahead.
You could have usually atoms combined that are electropositive and electronegative, or both neutral, or
Yeah. Right.
similar. How could you have H2? Like where they combine into a molecule.
Oh, that's a good question. No, that bothered chemists and physicists for a long time. To really understand that, you have to know more about electrons than I've told you so far. But what scientists are eventually going to discover is that these things I've been calling hooks, valence on atoms, are really the number of electrons that are involved in the bonding to other atoms. I'll try to explain that before the class is out, why gas molecules combine up and hang around in pairs. But it turns out to be, the answer to that question is actually pretty complicated. Okay, I guess I'll leave as an exercise for you to work out the mass of the electron. You'll find that it's pretty small, I think. And then I'll have more to say about what that means next week.